Okay, so good evening and welcome to the 12th live session for linear algebra, applied linear algebra. And um, in this session, we are going to look at few examples. And so, mostly these examples will be based on the contents of the final week, which was week 12 of the course. And in week 11, in week 12, we mostly explored the if you recall the lectures, we explored the um, weighted least squares solution or estimate, right? So, I mean, we had already seen the least squares approximation, how the least square solution is given, and when do we use least squares method, and um, a slightly modified version of the least squares is the weighted least squares, where we have a weighting matrix, right? And you can very well observe that if the weighting matrix is the identity matrix, then the weighted least squares reduces to your standard least squares. Okay, and then we also saw the use and application of Woodbury matrix identity. Okay, so it's WMI for short. So how it can help us to compute the inverse of uh, a matrix of the form some A plus UCV, right? We want to find the inverse of A plus UCV, and these UCV have some different properties. Like this is useful uh, um, whenever like A, the matrix A, is easily invertible. Let's say it's an identity matrix, and the matrix U is a tall matrix. The matrix C is a square matrix, and the matrix V is a wide matrix or a flat matrix. So overall UCV, this product, this is also a matrix which has low rank, and instead of doing all the computations of the inverse, this identity helps us, although the expression looks a bit complicated, but it helps us to find the inverse in less complexity, with less complexity. And we have looked at examples, so I'll also illustrate a similar example here in this session. And then we moved on to our analysis of the conditional Gaussian PDF, right? How is the, I mean, what are the parameters of the conditional Gaussian PDF, namely the mean and the covariance. So those are kind of like we have looked at the derivation and all. So yeah, I mean, you can expect some problems based on just using the formula and all. But in general, for today's session, I've kept some like basic proof-based examples and calculations from basic concepts of probability, from topics like random vectors and all, which we have already covered in this course and in the last week. I mean, in week 12 of the course. So in fact, this conditional Gaussian PDF analysis also involve a lot of analysis with the means, the covariances, random vectors and all. So I mean, it's good to have a basic understanding. I mean, good to have a understanding at a very basic level of these concepts. Then only you will be able to appreciate them at a more higher level. Okay, so let's get started for today's session. Okay, okay, okay. So this is week 12. I mean, session number 12. Okay. So let's look at the first question. Okay, so we have seen this type of case in the week 12 lectures. So we have a model uh, characterized by this equation y bar equals to ax plus v bar. Okay, now what are these y, a, x and v? So x is your transmitted signal. You can think of it as a transmitted signal, maybe some classical bit uh, that you want to estimate. Okay, and here in this case x is a scalar quantity. Okay, it's not a vector, it's a just a scalar that has to be estimated. Now this v bar is your noise vector, and it's a Gaussian noise vector, and also it's a independent and non-identically distributed Gaussian noise vector. Okay, so it's independent, it's Gaussian, and independence automatically implies uncorrelated, so that's fine. So the covariance matrix of this noise would be a diagonal matrix, because the off diagonal elements will be zero, because there are no correlation between the noise samples because they're independent, so uncorrelated, and they are also non-identically distributed. Okay, meaning that like the variances of the individual noise samples can be different. So the sigma 1 square, sigma 2 square, all these diagonal elements, they may be different as well, so they are non-identical. If they were identical, like the IID case, independent and identically distributed, then it's simply like sigma squared identity. That would be the noise covariance matrix, which we have already seen. Okay, and your y bar vector is the noisy vector of your observations or the outputs, right? And for this problem you are given what is y bar, what is the output vector of observations, noisy observations that you have. It's a 2 by 1 vector with the entries 1 and 2. If a is also a 2 by 1 vector with the entries 0.6 and 0.4, and this v bar, this noise vector, um, has these samples, let's say v of 1 and v of 2. These are actually random variables, v of 1, v of 2, and their variances are given to you. So the variance of v of 1 is sigma 1 squared, which is 0.5, and this variance of v of 2 is sigma 2 squared equals to 0.25. So this information is given to you. Then you want to estimate the transmitted signal AX using the optimal weighted least squares method. Okay, so what is the optimal weighted least squares or WLS estimate of X? And X is a scalar, so you expect a scalar uh, quantity in the answer as well for the estimate of X, and from the options also you can see all are scalar quantities. Okay, so let's solve this. We have seen similar example during the actual lecture. So and also like I hope people have, those who have registered for this course have received an email regarding the exam format and all. So what is the mode of the exam, whether it will be pen paper based or computer based, right? So last time I checked, I think for this course it will be computer based test, but anyways you can check that mail and have a look at it yourself. So the format of the pattern of the questions, be it MCQs or numerical answer types, everything is given there. So yeah, do check that mail in case you haven't yet. Okay, so in our question, what we are given is, this is your received vector, this is the noisy observation vector, right, at the output. This is actually of this form. Okay, so this is y bar. This is your matrix A. I mean, it's a column vector in our case, and this x is a scalar that you want to estimate, to be estimated, and this is the vector v bar. Okay, which is your noisy vector, I mean Gaussian noise vector, and these noise samples, which are random variables, Gaussian random variables v of 1 and v of 2, they are independent but not identically distributed. And what you are given is variance of the first noise sample is, I mean, denoted by sigma 1 square. So this means VAR means variance. Okay, I'm writing in short. So this is equal to, it's given as 0.5, and the variance of V of 2 sigma 2 squared is given as 0.25. And even if you look it at like the basic level, this y bar equals to ax plus v bar is what we have here, and here A is a tall matrix. I mean, in this case it's a column vector. Of course the number of rows is 2, which is more than the number of columns, which is 1. So it's a tall looking matrix, and whenever we have this kind of a situation for a tall matrix, we go for the traditional least squares solution. But in our question we are asked to find the weighted least squares, right? And the only difference is that uh, in weighted least squares we will have a weighting matrix in the expression of the estimate, but that is simply not present in the case of least squares. Essentially the weighting matrix is identity in the case of least squares. So this is a tall matrix, so this motivates us to go for the least squares solution for estimating x. Okay, but in case of weighted least squares, for weighted least squares, least squares is like ls, and for weighted least squares, which is wls, we choose a weighting matrix w, and I'll also mention, which I've already stated, like note that w is equals to identity for the standard least squares. So the for this kind of a situation, or before I tell you about w, the choice of w, what is the noise covariance matrix? So the noise covariance matrix, let's say if you denote it by some RV, right? That RV is nothing but sigma 1 squared and sigma 2 squared as its diagonal entries, and this is 0 0. Of course it is 2 by 2 because your noise vector is 2 cross 1 vector, and the off diagonal elements are 0 because the noise samples are independent, and of course which automatically implies they are uncorrelated as well. So this is nothing but sigma 1 squared is given as 0.5, sigma 2 squared is 0.25. This now you choose as we have seen in the lectures, we choose the optimal weighting matrix. Okay, optimal weighting matrix W is chosen as the inverse of this noise covariance matrix. Okay, and since this noise covariance matrix is a diagonal matrix, we can easily find its inverse. So the diagonal elements will be just converted into their reciprocals and the rest remains the same. So this is basically 1 by 0.5, which is 2, and 1 by 0.25 is 4. Okay. Of diagonal elements are 0. And now you need to find the estimate, WLS estimate. So the WLS, or weighted least squares solution, the estimate actually is given by x hat. So I'm denoting the estimate as x hat, which is equal to, we know it is A transpose WA whole inverse times A transpose W y bar. Okay. So the original model was y bar equals to AX plus V bar. So the estimate of x, which is denoted by x hat, the WLS estimate, the weighted least squares estimate, is given by this. And you see that this W, which is the weighting matrix, is sitting here, right? And if clearly your, for the least squares, this W would be identity. It's as if it is not present. Clearly for least squares, W is identity, and in that case your x hat is simply A transpose A whole inverse A transpose y bar, which we have already seen before. Okay, this is the standard least squares. Okay, okay. So now let's compute the WLS estimate. So okay, let's compute it part by part. So let's first find A transpose WA, what this is. So A transpose, so this is what we are trying to find. Okay, this. So what is A transpose WA? A, remember, was that column vector 0.6, 0.4. So you take its transpose and you get this row vector, and W you have calculated, which is the reciprocal of the noise covariance matrix. You got this as your W, the weighting matrix, and then you have A. Okay, so if you calculate this, you'll get 1.36. okay, it will be a scalar, because at the end of the day we are expecting x hat to be a scalar, because your original x which was transmitted was also a scalar. And it makes sense because this is 1 cross 2, this is 2 cross 2, this is 2 cross 1. So if you multiply 2 cross 2 with 2 cross 1, you'll get a 2 cross 1, and if you multiply a 1 cross 2 with a 2 cross 1, you'll get a 1 cross 1 scalar, right? And so what is the inverse of this? Because we need to find its inverse for the estimate calculation, so this is simply the reciprocal of this scalar, because it's just a scalar. Now let's find the remaining part, which is A transpose W y bar. So okay, did I run out of connection. Just a second, let me check. No, it's fine. Okay, so now the remaining part is A transpose W y bar. Okay, so which is A transpose again 0.6, 0.4. Yeah, W is 2004, and y bar was the noisy observation, which is 1 2. If you go back, this was y bar, and again if you just calculate this, you'll get 4.4, again a scalar. So therefore now you can find the estimate, which is the product of these two, right? So this is nothing but your A transpose WA inverse times A transpose W y bar, which is 1.36, sorry, the reciprocal of 1.36 times 4.4, and that is some 3.2353. Okay, this is your estimate of X, WLS estimate, weighted least squares estimate, and the correct answer is clearly option A, 3.235. So this. I don't think this is really hard to remember. Even if you try to memorize this formula, it's pretty straightforward actually. And if you recall, if you remember this formula, then you automatically can remember the formula for least squares as well. Okay, just in this case, there is a weighting matrix W, which is absent in the case of least squares because it's identity. Okay. Okay, so now let's move on to the second question. Okay, so for the second question, you are asked to use the Woodbury matrix identity to find the inverse of this matrix P, where P is defined as follows. So it's a sum of this 4 by 4 identity matrix and uh, this product of two vectors, right? So you have a column vector 1 2 minus 2 1 times its transpose basically, right? 1 2 minus 2 1 as a row vector. So this will also be a 4 cross 4 matrix. So for this, if you try to find, because we have to find the inverse, so if you try to go with the traditional process, then you have to uh, first find the overall result of the addition. So you can find the overall 4 by 4 matrix, and then again you have to compute the inverse of a 4 by 4 matrix, which is quite tedious, right? So it will involve a lot of computations. But so this is where this Woodbury matrix identity, or WMI, comes to our rescue. Okay, and as I said, remember, okay, let me just mention it here only. So recall lecture 65 where this was discussed. So when do we use, okay, the Woodbury matrix identity, or WMI for short? So whenever we want to find the inverse of a quantity that has this form, a plus ucv whole inverse. Okay, and under certain conditions. So this WMI technique is helpful when this A is a easily invertible matrix. For example, the identity. Okay, because we know the inverse of identity is identity itself. Okay, or maybe some known diagonal matrix, right? So finding its inverse is straightforward because we just to replace the diagonal entries by the reciprocals. And this U is a tall matrix, and this V is a wide matrix or a flat matrix having uh, less rows than columns. Okay, and overall this UCV has low rank. Okay, under this condition you can use the WMI, the Woodbury matrix identity, which is equal to A inverse minus A inverse U times C inverse plus VA inverse U whole inverse times VA inverse. So this might look very complicated with lot of terms, but if these conditions which I stated before are met, then this can be, useful, because the RHS might be easier to compute, okay, under these special cases. So let's see if in our question whether this is useful or not. It must be useful because you're asked to use the Woodbury matrix identity. So what do we have in our case? We have a matrix P, which is this identity matrix plus this. Okay, so you see here we want to find P inverse. What is P inverse? So this clearly, the first term here is identity, the 4 by 4 identity, and if I call this vector 1 2 minus 2 1 as some x bar, then this simply is the transpose of x bar, right? X bar transpose. And so what is essentially your P? So P is identity plus x transpose. Yeah, and I can also write this as identity plus x bar times 1 times x bar transpose. So this is just scalar 1. Okay, um, so now you see what is P inverse. This is simply identity plus this whole thing inverse, and now this has a similar form as that of A plus UCV whole inverse. Okay, so you compare with A plus UCV whole inverse, it's similar, and on comparing what you can get is your A is nothing but identity, your U is the vector x bar, C is simply 1, the scalar 1, V is x bar transpose. Okay, and the conditions are met. Like A is identity, which is easily invertible, it's the inverse of identity is identity itself. U is the x bar, which was our column vector, And a column vector is also a tall matrix. You can treat it as a tall matrix because it has only one column, but in this case it has 4 rows, so more rows than columns, right? It's a tall matrix, and V, which is the transpose of that, is now a wide matrix or a flat matrix with more columns than rows. Okay, so now we can make use of the Woodbury matrix identity, and we can expand this as, so what is P inverse is simply this inverse, which is, okay, I'm using this identity here. Okay, this RHS I'm just simply applying here. I know what is A, U, C and V in our case, and I'm just simply substituting that. So in our case, so the RHS tells you that it is A inverse, the first term is A inverse, so which means identity inverse because A is identity, minus, then we have A inverse into U, so A inverse, again identity inverse, into U, which is U is x bar, within brackets C inverse. So C inverse is simply, C is the scalar 1, so its inverse is simply 1 itself, plus V A inverse into U. So V, which is X transpose, A, which is identity, and what was the third term? Okay, so V A inverse U, right? So V is X transpose, A inverse is identity inverse, and and there was U, right? So this is X, yeah. So this whole inverse, and we have finally V into A inverse. So V into A inverse, which means this. So identity inverse is identity, yeah. So this is, okay, identity acting on X gives me X plus, and again this reduces to this, yeah, okay. So now this term here, X bar transpose X, this is basically the norm square, right? It's basically the inner product of X with itself. I mean, since we are in the real domain for real matrix, for real vectors, this is how the inner product is defined, and this is simply the norm square of X bar. So overall this quantity inside the brackets, it is 1 plus norm X squared, which is just a scalar quantity, right? And its inverse is simply the reciprocal of that. So this is identity minus this, and we have already derived this in class as well. I mean, in the lectures professor has derived this, okay. So now this will involve lesser computations, okay, because you see in our case the identity is the 4 by 4 identity, minus, so what about this scaling factor 1 divided by 1 plus norm X square? So let's find that first. So 1 divided by 1 plus, what is norm X squared? So norm X squared, what was X squared, I mean what was X bar, the vector, this vector was 1, 2, minus 2 and 1. So the norm square of that is simply the sum of the square of the elements, right? Because this is like in the real domain. This. So this part here is your norm x squared. Yeah. And times x transpose. So what is x transpose? This is simply your what was x, and your x transpose is this. Okay. Okay, so what do we have here? Minus, so this denominator, if you add the terms, you'll get 11, I think. 1 plus 1 plus 4 plus 4 plus 1, which is 11. So 1 divided by 11, and now if you multiply these two, this column vector with this, with its transpose, you'll get this matrix. And now it's just simple. Yeah. So I'm multiplying this scaling factor to the second matrix. And so this will give you 10 by 11 minus 2 by 11. And you can simply take this 1 upon 11, this factor outside, okay. So this is your answer. So we were able to avoid the complicated inverse operations and computations, and we simply needed to find this quantity here, identity minus x transpose whole divided by 1 plus norm x squared, right? Which was which we are able to do it in just 2 to 3 steps. That's it. So this is how it is useful. Okay. Okay, so now let's move to the third question. Okay, so yeah, now I'll just uh, illustrate few simple basic problems on all this this random vectors, covariances and all, because they are very much rigorously used in the derivations in our actual lectures as well. So maybe if you get your hands dirty with some of these basic examples, then you might appreciate the derivation and all, and the proofs and all. So yeah, and in fact this third question, I think it was already uh, discussed in during the actual lectures in one of the old lectures, maybe around week 5 or 6, something like that, or maybe before that. So here we need to find the covariance matrix. So the model that we have here is y equals to ax plus b, and where x is your n-dimensional random vector. Okay, so it's a n by 1 vector of random variables. Okay, let's say x1 x2 all the way till xn, and there is another random vector y, capital Y, which is expressed as ax plus b. Okay, where this A is a fixed m by n matrix and this B is a fixed m dimensional vector. Okay, so dimensionally this equation makes sense, right? Because y is m by 1, a is m by n, x is n by 1, so the product ax is m by 1, and you are adding b, which is also m by 1. So overall you are getting y as m by 1. Given this, you have to show that this cy is equals to a times cx times a transpose, where cx and cy are the covariance matrices of x and y respectively. Okay, we have seen this in our actual lectures as well. You can go back, but let's see. So this we have to prove actually. Okay, so cy is the covariance matrix of the random vector y, and Cx is the covariance of the random vector x, and we have to prove this relation. So let's look at it. So we have this random vector x. So x is a random vector. Okay, so it has a vector. It's a vector of random variables, and it is a n by 1 random variable, random vector, sorry. So you can think of it as some x1 x2 all the way till xn. So this is n cross 1. Okay, and these xi's, okay, these are your random variables. So you have an n dimensional random vector x, and you have this relation y equals to ax, y equals to ax plus b. Okay, this is the same x, okay, same random vector. So y is a m by 1 random vector, a is a m by n, fixed matrix, so it's a constant matrix. X, as you know, we have already written down, n cross 1 random vector, and your B is another m by 1 fixed vector. Okay. So you have to find the covariance matrix of y, the random vector y, and show that it is related to the covariance matrix of x, a transpose, like that, uh, in that relation. So let's first find the expectation of y, okay, because we will use that, we'll need that in our proof. Actually, we'll need that in our covariance computation. So first, or maybe before that, what I'll do is, first let's convince ourselves that we know what Cx means. It's the covariance, right? Okay, I'll just covariance matrix of the random vector x. Okay, here x is a random vector, so that is denoted by Cx in our question. And in our lectures, I think what we have seen is, this is nothing but, this has this notation. So we are finding covariance of x with itself. X is a random vector, and this is nothing but, how it's defined is expectation of, so x minus expectation of x, this is one term. Then we have x minus expectation of x whole transpose, so this. So what we have is covariance matrix of x, where x is a random vector, is this. Okay, we know this uh, from the discussion we had so far. We are familiar with this. So this is true for when x is a random vector. Okay, because the question of transpose arises only in the case of vectors, right? But if x was a random variable, this transpose would be absent. Okay, fine. So let me label this as equation 1, and now let us try to prove what we are asked to prove. So Cy, okay, what is Cy? The covariance matrix of y. So this is your covariance matrix of the random vector y. So we have already seen the definition of covariance matrix. So how Cy would be defined? It is simply the expectation of okay, maybe before that I'll also do one more thing. Okay, so I have y equals to ax plus b. So what is the expectation of y? This is simply expectation of ax plus b, right? And that is, since a and b are fixed, right? A is a fixed m by n matrix and b is a fixed m by one vector. So I can simply take it outside. So this is a times expectation of x plus expectation of b, which is same as b, okay, because b is a constant, right? So let me label this as equation 2. Now let me find the covariance matrix of my random vector y. This is cy, which is, by the definition of covariance matrix, expectation of y minus expectation of y times y minus expectation of y transpose, right? So, and this is nothing but expectation of, so now I'll use equation 2, because or maybe in the next step, so this um, or yeah, we can actually do that, here itself. Yeah, so this is nothing but expectation of, I'll substitute expectation of y and I'll substitute y, okay. So I know y is equals to ax plus b, I know that. And what is expectation of y? We have just calculated in equation 2. It is simply this thing. Again we have y minus expectation of y the whole transpose. So that becomes this, right? So I have used, since y is equals to ax plus b, and using equation 2. Using equation 2, I have substituted for expectation of y. Okay. So you can clearly see that this b and b gets cancelled. Again, this b and b gets cancelled. Now let me go to the next page. So this is nothing but expectation of, so from this first term we can take a as common. So this is a x minus expectation of x. Yeah, so this is your first term. Again, similarly we can take a common here in the second term, but we also have a transpose sitting outside. So this is a times x minus expectation of x, yeah, this whole transpose. Now I can also write this as a times expectation, a times x minus expectation of x. And now what about this second term here? So a times some x minus expectation of x, this product, you are taking the transpose of this product, okay. Here x and a, you can treat them as matrices. Basically x is a vector, but it's a special case of a matrix, right? So you have some PQ whole transpose form, right? And you know that PQ whole transpose is nothing but Q transpose times P transpose. So I can write this as this, since PQ whole transpose is Q transpose times P transpose. So now what do we have? Remember, A was a constant matrix, so I can bring that outside. Similarly, A transpose is also a constant matrix. I can bring that outside as well. So, and also, of course, I'm taking A transpose outside. So this is, and why I'm writing this, since A is a constant matrix or fixed. Constant or fixed matrix. Okay, so now what is this quantity here sitting in the middle? This is simply your covariance matrix of X, right? If you go back, covariance matrix of X is exactly defined like this in equation 1. That is why I wrote these equations in the beginning. So this is nothing but your Cx, covariance matrix of X. Okay, just a second. So this is nothing but your A times Cx, A transpose. Okay, this is exactly what we were asked to prove. Yeah. Okay, so now let's move on to the fourth one. And again, this should be known to you, but still, I mean, if you want to. So at the end of the day, what I'm trying to convince you is that although there are certain formulas or forms that you need to memorize, I mean, it's good if you memorize, um, but even if you are unable to memorize, you can use simple calculation and derivation to arrive at that form by yourself. Okay, so that is the motivation to discuss this basic, problems on random vectors and stuff. Anyway, so in fourth question you are asked whether two independent random variables are uncorrelated or not. If yes, then prove. We already know that it is fact, it is true that two independent random variables are uncorrelated. We are now talking about random variables, okay, not random vectors. So what this question is asking is, the answer is yes, two independent random variables are uncorrelated. But the converse is not necessarily true. The converse turns out to be true in case of jointly Gaussian. Okay. So independence, maybe I'll mention it here, implies uncorrelated. But uncorrelated not necessarily implies independence. Not necessarily. Okay. So, but we have to prove that as well. So let x and y be two independent random variables. Okay. To show that they are also uncorrelated, we can simply show that the covariance of x and y is 0. So they have no correlation or covariance between them, which means they are uncorrelated. So um, to show that x, y are also uncorrelated, we need to show that the covariance of x and y is equal to 0. Equal to 0. Okay. So let expectation of x be equal to mu x and expectation of y is equal to mu y. Okay, so they are random variables, so let these be their means. Okay, I'm using like a simpler notation. Instead of writing expectation of x, expectation of y always, I'll use a simpler notation, mu x, mu y. So what is covariance of x and y? This we need to show that this is equal to 0, right? So now we are talking about random variables. Okay, we are no longer talking about random vectors. So remember the formula that we used for random vectors, the covariance of random vectors, we used that transpose. Remember, yeah, here if you see question 1 here in the previous question, we use this transpose because we are dealing with uh, random vector. Okay, but here for random variable, this is defined as expectation of, we can avoid that transpose. Okay, we'll just keep that transpose. So this is expectation of this term times y minus expectation of y. Now no longer there will be any transpose, right? And it makes sense because it's no longer a vector, so it's just a single entry, so it's a random variable. Remember, random vector is like a collection of those random variables tagged as a vector. then in that case you talk about transpose because you are dealing with vector, but here it's simply no transpose arises in this case. Okay, so now this is expectation of, using our notation, so expectation of x is mu x, expectation of y is mu y, right? This is covariance of two random variables x and y, not random vectors. Okay, so no transpose, that's why. So this I can multiply this two terms, so there will be four terms. So first term is xy minus x times mu y, so x times mu y minus mu x times capital Y plus mu x times mu y. Okay, and now using linearity of expectation, I can write this as expectation of xy minus expectation of okay, using linearity. Okay, so now what about expectation of xy? Expectation of xy, I can write it as expectation of x times expectation of y. Why? Because x and y are independent. That is the given condition. Okay, whenever we have independence, then we can like multiply them together. Even in terms of probability, the probability of x intersection y is simply product of the probabilities, probability of x and y, right? So for expectation also, expectation of x y is equal to expectation of x times expectation of y if x and y are independent. And for the second term, this mu y is like a constant, so you can bring this outside. For the third term, mu x is a constant, so you can bring that out of expectation. And the fourth term, you see expectation of mu x times mu y. So mu x, mu y are constants, their product is also constant, and expectation of a constant is that constant itself. So this is mu x times mu y. Okay. Now how this happened, how I can write, how I was able to write it as product of expectation using I mean not, since x and y are independent. Okay, using independence actually, since x y are independent. And what about this guy here, expectation of x, this is mu x. What about expectation of y, this is mu y. So what do we have here? And of course this is also expectation of x, expectation of y, right? So if I go back to the next page, so this is expectation of x times expectation of y minus expectation of y times expectation of x minus expectation of x times expectation of y plus expectation of x times expectation of x. So this gets cancelled. This also gets cancelled. Have 0. So covariance of x and y is equal to 0, which means x and y are uncorrelated. So therefore what we just showed, independent random variables implies uncorrelated. Okay. Okay, now in this fifth problem, we are given a random vector x. It's an n by 1 random vector, x1, x2 all the way till xn. So x1, x2, xn, all these are random variables, right? They are stacked together as a column vector to form this random vector x. Then we have to show that the covariance matrix of x, right? The covariance matrix of this random vector is given by this form. It's a matrix of this form. Okay, where this var of xi denotes the variance of xi, and cov of xi comma xj denotes the covariance of xi and xj, the standard notations that we have seen before. So like this form of the covariance matrix should be known to you. We have seen this like before, but in any case, if you are wondering like, okay, why do I have to remember this, memorize this? My point is, even if you are unable to memorize, I'll show you the derivation now, so you can easily derive it yourself also, even if you are unable to memorize it. Okay, all right. Okay, so we're in the fifth problem. Okay, so x is given as x1, x2 all the way till xn. Okay, so this is a random vector. All right, so what is the covariance matrix of this random vector, right? Covariance matrix of x is, if I denote it by cx, is nothing but expectation of x minus expectation of x times x minus expectation of x transpose, because now we are dealing with random vectors, so we have to use this transpose. Okay, right. So now all right, so what is from here, what is expectation of x? Since expectation is a linear operation, so I can write this as expectation of x1, expectation of x2, so on till expectation of xn, right? So what is x minus expectation of x? So this is simply x1 minus expectation of x1, x2 minus expectation of x2, all the way till xn minus expectation of xn. So this is your x minus expectation of x. And what about its transpose? Its transpose is simply, so these are the entries, right? The first entry, second entry, nth entry. So its transpose is simply the row vector. Now this is the first entry, second entry, and nth entry. So this here is n cross 1, this is 1 cross n. Okay, so this is n cross 1, again n cross 1. Now for finding the covariance, we have to multiply these two terms. Inside expectation, we have to multiply these two terms. So what is, so my Cx, which was my covariance matrix of x, is nothing but expectation of x minus expectation of x times x minus expectation of x transpose. So this is nothing but, I have already found the form for these matrices, for this x minus expectation of x and its transpose. So this is expectation of, what is x minus expectation of x? This vector, right? And its transpose is simply this. So now I can carefully multiply them. So this is n by 1, this is 1 by n, so their product will be n by n matrix. So the first term of that n by n matrix, the 1 comma 1 term will be x1 minus expectation of x1 squared. Second term would be 1 comma 2th term would be this times x2 minus expectation of x2, right? So on all the way till x1 minus expectation of x1 times xn minus expectation of xn. What about the second row? So this will be x2 minus expectation of x2 times x1 minus expectation of x1, right? and the 2 comma 2th element will be x2 minus expectation of x2 whole squared. So these square terms are occurring in the diagonal entries, right? And all the way till x2 minus expectation of x2 times xn minus expectation of xn, and you can go all the way till the nth row where the n comma 1th element would be and the n comma 2th element would be and finally the n comma nth entry would be the square term, this. So now these square terms you see which are occurring in the diagonals, in the diagonal entries, they are actually the variances. I mean, once you take the expectation inside, look at the first 1 comma 1th term. If you take the expectation inside, you get expectation of x1 minus expectation of x1 the whole squared, so which is nothing but the variance of x1. That's the definition of variance, right? And what about the off diagonal elements? Say this off diagonal element, say this one, 1 comma 2th element. What is this? This is nothing but this term here. So your capital X was the random vector and it had x1 x2 all the way till xn as its entries. So x1 x2 all the way till xn, they are random variables individually. And for random variables, remember the definition of um, covariance. So maybe okay, before I go to that, I have to take the expectation inside. Okay, so maybe in this step only I can write, right? So my point was like this diagonal entries are the variances, and the off diagonal entries, if you consider, this term here. So once you take expectation inside, so expectation of x1 minus this term sitting here, this is nothing but the covariance of x1 and x2, where x1 x2 are the random variables. Covariance of random variables, not random vectors, because we don't have transpose here, right? And similarly you can do it for the rest of the off diagonal entries. And for the diagonal entries, that is more easy to observe. So if you take expectation inside, so you have expectation of x1 minus, and this is simply the variance of the random variable x1. Maybe instead of curly brackets I'll use first bracket. Okay. So all these diagonal entries will contain the variance terms. So what you will get ultimately is if you take expectation inside the variance of x1 and the off diagonal elements, you will get the covariance terms. All the way till covariance of x1 comma xn, right? Yeah. What about the 2 comma 1 element? That is the covariance of x2 and x1. Covariance of x2 comma x1, and 2 comma 2 is the diagonal entry, so again variance of x2 all the way for the nth row. You will have covariance of xn comma x1, covariance of xn comma x2, and the n comma nth entry would be the variance of xn, and this is your n cross n matrix, and this is exactly what has been asked to prove. So the diagonal entries consist of the variance terms, and off diagonal entries will have the covariance terms. And it's obvious, whenever we remember the first question where we looked at the um, noise vector, in the first question, this v vector, noise Gaussian vector, we said that since it is independent, it like in the question it was given this noise is independent, so independence implies like uncorrelated, so there was no correlation between these noise samples, so the off diagonal elements of the covariance matrix which contains the covariance terms are zero in this case. You see, the noise covariance matrix that we obtained here was a diagonal matrix only, and the diagonal entries were given by the variance which we just derived now. Okay. There are certain things that you must know, you must remember. For example, what is the definition of covariance? What is the definition of covariance matrix? Okay. So this you have to remember, right? And we saw like the subtle difference. If we are talking about random vectors, then this is the definition. This transpose will be present. And if we are just talking about random variables, then this transpose won't be present. Okay. So this is also done. Now moving to our last problem for today, I believe. Again, this is like very basics of probability theory. And since we discussed like the jointly Gaussian PDF, since it was discussed in the week 12, so this is also a similar question. It's based on that, although it doesn't talk about the conditional Gaussian, but yeah. So you are given x and y which are jointly continuous Gaussian random variables, and their joint PDF is given to you. Okay, it has two forms depending on the range of x and y. So the small x and small y are the values of the random variables that capital X and capital Y, which are the random variables, can take. Okay, so capital X, capital Y are the random variables, and small x and small y are one instant or one value of those random variable. Okay, given this, you have to find the variances of x and y. Okay, so how do we do that? Okay, so whenever we see this PDF, we think of some expectations and also, and at the end of the day, we have to find the variances of x and y. What is variance of x and what is variance of y? And we know that variance of x is given by expectation of x squared minus the square of expectation of x. So which means the mean squared value minus the square of the mean value. This is known to us. And similarly, you can do for the variable y as well. So once you know the expectation of x as well as the expectation of x squared, right, the mean squared value as well as the mean value, you can get the variance. And you are given the but for finding expectation of x or expectation of x squared, you need the PDF of x, only x. Okay, but what you are given is the joint PDF. So from joint PDF, first you have to find the marginal PDFs of x and as well as y. So you have to find the PDF of x, PDF of y, and then correspondingly find their expectations and squared mean value and so on, and finally find their variances. So that's the process. Okay, for the sixth question, so x and y are jointly continuous, because in this case they are continuous random variables. Because you can see, like, yeah, they are continuous. They can take a continuum of values. They are not discrete random variables. So in our expectation calculation, basically we have to integrate. If they were discrete random variables, we could have taken summation to find the expectation. So they're jointly continuous random variables with joint PDF Okay, so this is the joint PDF. So what is the variance of x and variance of y? This denotes variance of x. This is variance of y. So as I said, before we proceed, we need to remember that variance of x is given as expectation of x squared minus expectation of x squared, right? I mean, why this is true? Because I mean, we know this, but anyways, like we know that expect what is variance of x, that is defined as expectation of x minus expectation of x the whole squared, right? Though these were the diagonal entries in our previous case, right? Previous question. So what is this? This is nothing but expectation of, so x minus y whole squared, so this is x squared minus 2 times expectation of x times x plus expectation of x squared, right? So this is expectation of x squared minus, now I'm using linearity of expectation, so times expectation of x plus expectation of x squared, so that's some mu x squared, right? So it's the same thing even if you take its expectation. So this is expectation of x squared minus twice expectation of x squared plus expectation of x squared. So this is nothing but expectation of x squared minus expectation of x squared. This is exactly what I have used here. And similarly, variance of y is expectation of y squared minus expectation of y squared. Mean of squared value minus mean value squared, right? Because expectation is nothing but mean. So mean squared value minus mean of, like, square of mean value, that gives me variance. Great. So for that, in order to find these expectations, we have to first find, as I said, the marginal PDFs. First obtain the marginal PDFs of x and y. So only the PDF of only x and PDF of only y separately we have to find. So how do we do that? Marginal PDF of x denoted by f x of x. So no longer any joint. So this is only x, its PDF. So this we can find from the joint PDF by integrating that. Why integrate? Because we are in the continuous, in the domain of continuous random variables. So we have to integrate the joint PDF, right, with respect to dy, okay, and y running from minus infinity to infinity. But in our case, you see this joint PDF is defined only from 0 to 1, x and y going from 0 to 1. In only that case it is like non-zero. In the other domain it is 0. So what matters here in the integration is only y growing from 0 to 1. And for that domain it is defined as, in that interval, the joint PDF is defined like this, correct? And this gives you, so we are integrating with respect to y, so all x terms are constant that we can bring outside, and I can split this summation into two, sum of two integrals. So I'll have this is 3x squared by 2, and this part becomes 1 plus I'll have this, so which is this. And this also exists, I mean this is also true when x is from 0 to 1, because the joint PDF is of this form only when like both x and y are lying between 0 to 1, right? Okay, I mean go to the definition here, both x and y lying in this interval 0 to 1, then only it is non-zero and the joint PDF is of this form, 3x square by 2 plus y, otherwise 0. So this is the joint PDF of, sorry, this is the marginal PDF of x, what we have found just now. Now we can go ahead and find the expectation of x or expectation of x squared and so on. But anyways, let's find the marginal PDF of y as well before that. So in a similar way, marginal PDF of y is denoted by this. Again, what we will do, we will integrate the joint PDF of x and y now with respect to x. So x now runs again from 0 to 1. From 0 to 1 only, that was non-zero. Okay, so this is oh, sorry, this won't be 3 here, this will be 2. Yeah, so this is half plus y, and again y runs from 0 to 1 because the joint PDF is 3x square by 2 plus y only when both x and y are in that range of 0 to 1. So this is how, and for other outside 0 to 1 interval of y, this marginal PDF of y is 0. Okay, so here what it means is the marginal of x, what we got before, is 3x square by 2 plus half, right? So 3x square by 2 plus half only when x is within this interval, 0 otherwise. Similarly for y, which we just got now, the marginal of y, marginal PDF, is half plus y whenever y lies within 0 to 1 and 0 otherwise. Okay, now we will find the expectations. Okay, so first let's find expectation of x. How do we find expectation of x? From the PDF, we basically have to integrate in this case because they are continuous random variables. Okay, so x times the PDF dx, x running from minus infinity to infinity, this is the general definition. This is for continuous random variables, and for discrete you can very well guess, I think I have already mentioned, expectation of x would have been summation instead of um, integration. And in that case, in the case of discrete random variable, we don't call it PDF, but we call PMF, probability mass function. We don't call it probability density function, unlike the case of continuous random variables. Discrete time, we call it as probability mass functions. Okay, right. So let's come to this integral. So this is, again, what is f of the fx of x, the pdf of x, that is effective only in the interval 0 to 1, remember, and outside of 0 to 1 it is 0. So this limit of integration is only effectively from 0 to 1, x times, what is fx of x, 3x square by 2 plus half dx. Okay, again you can just split the two summations. So you get 5 by 8. Yeah. What about expectation of y? Similarly, you just integrate this quantity here. So that is nothing but y going from, again, the effective limit of integration would be from 0 to 1, because we have seen that the PDFs are defined only from 0 to 1, otherwise they are non-zero, and the form of the PDF of y is half plus y in that limit. So this is half y dy 0 to 1 plus y square dy 0 to 1. This is half y square by 2 0 to 1 plus y cube by 3 0 to 1. So this is half times half plus 1/3, which is 7 by 12 if you calculate. Okay, expectation of x and expectation of y we have calculated. Now we also have to find the expectation of x squared and expectation of y squared, because we will need them to find the variance of x and y. So let's do that. So now expectation of x squared is also similarly x squared times the PDF of x dx, x running from minus infinity to infinity, and again effectively x runs from 0 to 1, we know, and the form of the PDF of x was 3x squared by 2 plus half dx. And if you calculate this integral, again similarly you can do that. This is 7 by 50. Okay, Similarly, expectation of y squared is nothing but y squared fy of y dy, which is again effectively from 0 to 1 y squared, and fy of y is half plus y dy, and if you calculate this you will get 5 by 12. Now we can bring all this together and find the variances. So variance of x is expectation of x squared minus expectation x squared. Yeah, so this is what is expectation of x squared, 7 by 15. What is expectation of x? Go back, expectation of x is 5 by 8, so this 5 by 8 squared. Okay, so this is 7 by 15 minus 25 by 64, and that will give you 73 by 960. So I'm keeping it in fraction. You may write it down to some decimal places. Okay, and what about variance of y? Again, expectation of y squared minus expectation y squared. What is expectation of y squared? We have calculated it is 5 by 12, and expectation of y we had calculated it was 7 by 12, so we take the square of 7 by 12, so this is 5 by 12 minus 49 by 144, and that gives you 11 by 144. Okay, so this is the answer. These are the two variances. So let me also write down finally. Variance of x is 73 by 960. Variance of y is 11 by 144. This is your answer, right? So with this we have come to the end of today's session. So only basic things, basic calculations and concepts of covariances, means, expectations, random variables versus random vectors, right? What is the formula of covariance matrix and so on. We have analyzed everything in details, right? So hopefully this will help you in understanding all the derivations, and also you would be able to derive things on your own in a better way, hopefully. And we have also seen the contents from week 12, namely the Woodbury matrix identity, how we can use that efficiently to compute uh, uh, the inverse, right, in an efficient way using the identity. And also we have seen how the weighted least squares approximation works, right? So that's it for today, and we will have one last extra session on next Friday 6 to 8 p.m. So we'll meet again, and that will be the last session. So yeah, and again, as I already announced before, just don't forget to check your email that you would have received regarding the exam format and all, so that will clear all your doubts regarding the pattern of exam, the mode of exam and all. Okay, all right, so let me stop the recording and we'll meet on next Friday. Thank you.